Thank you very much, Professor Chong and Professor Choi, for inviting me to Singapore. It's not the first time I've been here, and I hope there will be many future times. What I want to tell you about today is a broad spectrum of maths. I want to show you what can possibly unite the chap on the left there, who's Euclid, a Greek mathematician from around 300 BC, with the chap on the right, who's Alan Turing, famous for his work on cracking the Enigma code in the Second World War. What is the golden thread that can connect these two people over 2,000 years? And somehow it's the search for truth. In a world where we're surrounded by confusion and by people that try to distort the truth for their own political ends, and the term fake news seems to have gained an alarming currency, perhaps truth and what it means in maths, this idea of proof, is more important than ever. And I hope to give you some idea of that in my talk. Well, let me start with something defiantly classical and defiantly ahistoric. This is Raphael's fresco, The School of Athens, that collects together a huge pile of notable Greek philosophers. In the middle, you can see Plato talking to Archimedes. Euclid, if you look carefully, is down here with his slate. And Diogenes, famous for his lack of attention to his personal appearance, is there in the middle. So these are all searchers after truth. One of the most famous, perhaps, is Socrates, who's commonly thought to be this figure there. I'll have more to say about Socrates later, but I'm sure you know what Socrates is most famous for. So what I want to start with is this idea of a prime number. So a number is prime if it's at least 2, and it's only divisible by itself with 1. So the first few prime numbers are here. It starts 2, 3, 5, 7. 6 is not a prime, because 6 is divisible by 2. In fact, no even number is a prime, except for 2, because they're all divisible by 2. And I put them in a spiral for no terribly good reason, but perhaps it fits a few more of them on this slide. So there are all the prime numbers up to 113. Okay. Here are a few more. So I was just Googling for, I was saying, where can you find lots of numbers? And I thought, well, there's this strange game the Americans play that looks a bit like a barroom brawl, but at least sort of conducted within the environs of this strange thing that they kick around. So here are some of these experts at this game, and there's exactly one of them has a prime number on their shirt. I don't know if this was part of the team selection. Which one? Well, it's not 10, because 10 is even. It's not 57. 57 feels a bit more primey, maybe, but no, 57 is 3 times 19. 25 isn't prime, because it's divisible by 5. It doesn't have to be a different number, it can be 5 both times. So has everyone found the prime number? It's 31 in the centre there. It's the prime number there. 1 is not prime. Says who? Well, I'm afraid this is slightly unsatisfactory, maybe. I'm just going to have to say, we thought about the issue. Mathematicians have debated it for 300 years. 300 years ago, perhaps 1 was prime, but now we understand things a bit better, and really things work out much more neatly if 1 isn't prime. So, okay, if you would rather 1 is prime, that's fine. I'm not going to pursue you home and argue the case, but nowadays 1 is not considered. So there are the prime numbers up to 113. Here's a few more, up up to 211. By the way, I think this is a talk to a general audience, but I can supply a few mathematicians here as an exercise for them. Why are they, on the whole, organised along these straight lines? And how did I program this diagram to create that effect? Here they are up to 2017. It seems to be appropriate talking about primes because this is a prime year. How long are we going to have to wait for the next one? We'll find out at the end of the talk. But it's a while, so you should enjoy it. Because next year, will be an even number. So the question I want you to think about is, are there infinitely many primes? Can I keep on creating diagrams like this that will have more and more prime numbers? Because the prime numbers do get sparser. There's big gaps. From 1973 to 1979, 1979 to 1987, the gaps certainly get bigger as you go to larger and larger numbers. So does this mean that the primes are eventually going to stop? There'll be some largest prime, and beyond that, nothing more. Or will there always be a new prime number? Here's the sequence. 2027 is the next one after us. 2029. 1,000,000,007. That's the first prime after a billion. So, does this sequence ever stop? Or maybe there are infinitely many. Have a think in your own brain. If you haven't thought about it before, you've now got a lovely chance to just think for a moment. So I'll try to shut up. Well, what I want to show you is Euclid, so a mathematician that lived 2,300 years ago. I want to show you Euclid's proof that there are infinitely many primes. Now, proof is something that is unique to pure mathematics. Other sciences, physics, chemistry, they have the inductive method and the experimental approach, which is, of course, enormously powerful and is responsible for so many of the amazing things in modern life that we now take for granted. But no other subject is anything quite like mathematical proof. And a mathematical proof is not something to be scared of. It's simply a reasoned argument that is intended to convince you, a skeptical but intelligent person, what I have to say is correct. And you should be skeptical. If you can't see how one thing follows from the next, that would be an excellent time to ask a question. And the standard of proof, how much do I want to convince you? Well, we lock people up on the standard of reasonable, beyond reasonable doubt. But I want to convince you beyond even that. You should have no doubt whatsoever. And if you are left with doubts, well, you blame me. So let's see how the argument works. The first three primes are 2, 3, and 5. I'm going to multiply them together. I get 30. And then I'm going to add 1. So I'm now looking at 31, the guy in the middle of my picture. Now, if we divide 31 by one of these primes, 2, 3, or 5, there's always going to be a remainder. It doesn't divide exactly. There's a remainder of 1. Because it's 15 times 2 plus 1, and it's 10 times 3 plus 1, and it's 6 times 5 plus 1. And that was almost inevitable, because that's how I constructed 31. I multiplied those numbers together, and then I made sure there would be a remainder, because I added 1. So 31, it's a number, and it's not divisible by 2, 3, or 5. But it must be divisible by some prime. So I've given you a machine that creates a new prime. In fact, 31 is a prime number. Let's have another go. There are 6 primes go up to 13. So I multiply them all together, and I get 30,040. I add 1, so I'm now looking at 30,000 and 31. And for the same reason, this will have remainder 1 when I divide it by those first 6 primes. So it's 2 lots of 15,015, 3 lots of something, 13 lots of something, always plus 1. So this big number, 30,031, it always has a remainder when you divide it by the first 6 primes. But it must be divisible by some prime. So therefore, there is a new prime. It's not one of these first 6. In fact, in this case, the number I got isn't a prime itself. It's a product of 59 and 200. But these are both primes, and they're new primes. So Euclid's argument is simply to do this, but in general. And I'd like to demonstrate it to you by imagining a little dialogue. So Socrates here on the left is famous for his dialogues. He didn't write anything down. He would do very badly at a modern university because he refused to publish. He thought that you could explain things best just by talking to people. And not even really talking to people as I am now, but talking one-on-one to people, to really convince them that what he had to say was true. And we know of his work mainly because of his disciple Plato, who wrote down his dialogues. So I'm imagining a little dialogue between Socrates on the left and Euclid on the right. Socrates, I think. What does Socrates think? This is a complete diversion, by the way. He's famous for the cogito argument. I think, therefore I am, which is in some ways the first theorem of philosophy. You can trick me about many things. Maybe I'm sure you're convinced that you're listening to me droning on in a library building in Singapore, but just possibly you're having an exceptionally vivid dream and you're not really here at all. But Socrates says, there's one thing that you cannot trick me about. You cannot make me believe that there is not thinking going on. Because to believe that there's no thinking going on requires thought. So we can be certain that there is thinking. Let's imagine that Socrates thinks there are only finitely many primates. So he's prepared to make a list that he thinks might well be all of them. P1 up to PR. And then Euclid says, please consider this number, big N. So you do exactly what I did before. You take these numbers, you multiply them together, and then you add this very important, this red remainder of 1. Socrates, if I must. I don't quite see why you're telling me to do this, but I'm willing to follow your argument. When we divide Euclid's number by these primes, we always get the remainder 1. That's how I constructed it. Socrates is forced to concede this point. But now Euclid can say n is divisible by some prime. Every number is divisible by some prime number. So n is divisible by some prime which is not in Socrates' list. And therefore Socrates' list was incomplete. There cannot be finitely many primes. So there are infinitely many primes. Well, that's it. I hope you enjoyed the proof. It will be the only one. But as mathematicians, we care enormously about proofs. And you might be surprised at what the scope of modern mathematics is. I've given you a very classical example from what's now part of number theory. But as mathematicians, we care about all sorts of things. We care about codes, I'm going to show you some later, and cryptography, how you can communicate securely. Pure mathematics has become an enormous subject, rich in geometry, analysis, and algebra. I'm here for a wonderfully organized conference in my special area. You could ask me about that at the end. As a little diversion, I want to explain that mathematicians can even classify juggling patterns. So this is the three-ball cascade. Is the three-ball cascade fundamentally different from this? No. You can probably hear that the rhythm of my hands is not changing. Is it fundamentally different from this? Well, actually, no, although the difference is about 8 months of careful practicing. Is it different from this? Well, yes, you could probably hear that the rhythm changed. So you can classify juggling patterns. But mathematics is an enormously rich and vibrant subject. So to get on to the codes, I'd like you to play a little game. So take a friend, the person next to you if you aren't yet acquainted. One of you think of a number between 1 and 15, and the other person should try to guess it. But you must guess it in a very specific way. You must only ask yes-no questions. And when you're certain of the number, you can tell them you know their number. And try to do it as efficiently as possible. Ask us a few questions. And we'll see how many you need. Okay, then let's see how you all got on. So I'll ask you to put up your hands. Who here has an impressive psychic read and did it in one question? There's usually someone. Okay. Who did 2 questions? 3 questions? Okay, a few people. 4? Okay, 5 of you. 5? Okay, 6? More than 6. Okay. Well, I have to tell you that if you did it in 3 questions, well done, but you got slightly lucky. Another strange game, which is arguably a British export, is golf. In golf, there's this idea of a par score, which is what a professional player can expect to make if they're playing reasonably well. So the par score for this game is 4. And let me show you why. So here is a mathematical tree. Mathematical trees often grow downwards. It's not quite clear why. Perhaps we should get out more. But anyway, so here is a tree with 15 possible numbers on it. And you can see that all we have to do is ask you, is your number left or right? Okay, that's not yes, no, but left or right, yes or no. It's the same thing. So, suppose your number was 12. I would ask you, do I go left or right? You would say right, left, and then I would know your number. And because all the leaves, which are of course at the bottom of the mathematical tree, because all the leaves are at 4 steps away from the root, which is of course at the top, you know that I may find out your number in 4 questions. I've explained my strategy to you completely, and there's nothing you can do to avoid it. I won't win in 3 questions, but I can promise to win in 3. Now, we'll come back to this game later, and I'll ask you to play it again when you're allowed to buy. But first of all, let me show you what the connection is with our modern lives. So we are completely dependent on computers. Your mobile phone is by the step. I'm sorry? Oh, I'm sorry. Isn't that any better? Can you hear me at the back? Put up your hand if you can hear me at the back, please. Am I too loud at the back? Okay, right. So, I wasn't making a very profound point. I was saying that our modern lives are completely dependent on technology. But I think many people have very little idea just what computers are doing. And don't be powerless. Learn to program your computer. Get some feeling for what it's actually doing with your personal data. And the story all starts with these bits. Everything in your computer has to be represented by zeros and ones. Okay, that's a slight mathematical simplification. I do know that there are transistors involved, but let's think of it as zeros and ones. So here, for example, is how your computer stores the number 12. So it's storing it as the sequence of choices. Here are the 4 questions you might ask phrased to give yes-no answers. And it all leads down to this number 12, which is represented in binary as 1100. Because you go right, 1, you go right, that's another 1, and then you go left twice. And you can see the binary representations of all the numbers up to 15. I've included 0 there, because from the computer's point of view, 0 is a very natural place to start counting. 0 binary is just 4 zeros. Here's another example. This is a bit of Shakespeare in binary. Good, isn't it? So full of the richness of human life, the pathos of the character's almost desperate dilemma. Would you prefer it in English? So this is Hamlet's famous soliloquy, to be or not to be. What is the most common character in Shakespeare's soliloquy? I'll show you some of them. Here are the T's. They're all in red. The most common character is in purple, which you can see is represented in binary by the number 32, which is 001, a bunch of zeros. Why so many zeros? Why does 32 have so many zeros? What's special about 32? And what character is 32? Right, it's a space. It really doesn't work without the pauses. To be or not to be. No, you have to wait. So the space is encoded by 32 in binary. Here's another example, chosen almost at random from the bits of code lying on my computer. This is part of the machine code for Microsoft Word, my least favourite computer program. What I want you to notice is that there isn't really very much difference. They're all just zeros and ones. And this is why computer viruses exist, because it's very hard to separate the data that you want from the computer programs that process it. You can get confused between one and another. You think someone has sent you an email with a new, undiscovered Shakespearean sonnet. Wonderful, you think. I shall double-click this immediately. And then, unfortunately, it turns out to be a virus poised to take over your hard disk or leak your personal data. And of course, modern operating systems have ways of protecting you against this, but they're not completely infallible. And when I first got my new laptop, it refused to let me run programs that I had written myself on the grounds that they might be computer viruses. I consider this to be a violation of my human rights. Fortunately, I was able to turn this option off, although it has a habit of coming back on. And I find it a scary thought that in 15 years' time, you might buy a computer and find that unless you have a license or pay a fee, you're not allowed to program it. That would be a very sad thing in life. Everything is bits. Books, music, the computer programs that operate on it, even bitcoins. I've given this talk for several years, well, bits of it. I used to say, isn't it remarkable that a string of bits on your hard disk can be worth several $1,000s? Well, now worth several tens of $1,000s. This is the Bitcoin price over the last week. You can now trade Bitcoin futures, which is perhaps one reason why it's been so volatile. You can ask me more about Bitcoin at the end. Now, we have all this data represented by these bits, but there's a problem. We have to move them around the place. Moving them around the place could mean having a conversation on your mobile phone. It could be a space probe transmitting from the outer solar system all the way back to Earth. Or it could mean moving them not in space, but in time, writing your data onto a CD and then keeping it. That's a form of moving data. And whenever you do this, there's a chance that there will be an error. You'll write down a 0, or you'll send a 0, but it will be received at the other end as a 1. Or it could happen the other way around. How can we communicate reliably when this might happen? It seems to be a bit of a secret just how often errors occur with mobile phones. But as a rough approximation, if you're on 1 bar, the lowest strength, then about 1 in 10,000 bits is going to get flipped. About 1 in 10,000 times, what you send will not be what is received. And this is a disaster. If you send the machine code from Microsoft Word and a single bit is flipped, it will not work. Okay, what changed? It will not work in an even stronger sense. Nothing will work at all. So we have to have a way of getting around this. Let me show you how it works with another little dialogue. So I have Alice from Alice in Wonderland, and I have Bob the Builder. Alice wants to send a message to Bob. A little Shakespearean aside, my number is 12. Bob didn't hear that. In fact, Bob is only allowed to hear the bits 0 and 1. So what Alice could do is she could say 1100. That is 12 in binary. But Bob might not hear that. He might hear 1000. I've just changed 1 bit. But that means that what Bob hears is not Alice's number, because 1000 is 8. No, that's wrong. What did you say? Oh dear, this isn't working very well. Let's have another go. So now Alice is going to send her message with a bit of extra redundancy. So let's suppose that Bob hears this. He hears 1 3 times, then he hears 101, then he hears 0 3 times, then he hears 001, and he guesses that Alice has been saying the same thing 3 times over. So when Bob hears 101, he thinks, okay, was Alice trying to tell me 1 or 0? Probably it was 1, because although there was 1 error, we don't expect everything to be wrong. 1 error is less likely than 2 errors, sorry, is more likely than 2 errors. So Bob will guess that it's 3 repeats from 1100, and therefore Bob will get Alice's number. That is the basic idea of coding. You put in some extra redundancy in your message so that when these errors occur, you can still decode reliably and work out what Alice was trying to tell us. Let's see how it works in the context of the liar game. So I'd like you to play this liar game where you think of the number, again between 1 and 15, or let's allow 0 now that you know about binary. So a number between 0 and 15, and try to guess it. But this time you're allowed to lie, but please only lie once. So lying is like an error. When I send 0, I can lie deliberately and make you hear 1, or like I was doing earlier, I can just be mumbling and unclear, and you're not sure what I'm saying. Either way, it flips a bit. So let's see how many questions you need this time. George Auto, okay, thank you. So let's see how many questions. Who did this in 1 question? That should be impossible because you would just lie. Who did this in 2? That should still be impossible. Who did this in 3? 4? 5? Okay, 1, 2, 6? Okay, a few more. 7. 8. 8's quite popular. 9. Okay, 10. More than 10. Right. Okay. Well, the par score for this game is 7. If you're playing this game against me, I would win in 7 questions. I'll show you how in a moment. And if I had the secret number, well, unless you got lucky, you wouldn't be able to force it out of me in fewer than 7 questions. But let's see an easier strategy to begin with. Let's see how we can win in 12 questions. So I simply use the Allison-Bob code. I would make my first question, what is the first bit of your number? So I'd ask you to find your number. Let's say your number's 12, so it's 1100. And I ask, what's the first bit of your number? Let's say you say 1. And I ask again, what's the first bit of your number? And you say 1. Well, by now I should actually know, but I'll ask again, what's the first bit of your number? And you say 1. And by the end of this, I've got the complete code word, this full 12-digit, 12-bit long expression that encodes the number 12. And we saw that this Allison-Bob code can deal with one error. It can deal with more errors quite often, but it can always deal with one error, because if you lie, if you say 101, well, I'll know 1 was more popular than 0, so I'll know that the first digit was 1. So you should certainly have been able to win this game in 12 questions. But 12 isn't a terribly good score. You can win in 7 questions. Let me show you how. So Richard Hammond was a pioneer of early computing, and he invented the code we need. So it's a one-error-correcting binary code with 16 code words, so it can encode the numbers from 0 up to 15. And he invented it for a very practical reason. He had to program his early computer, which was not as convenient as things are now. You program this computer by feeding it in a roll of paper tape that was strategically punched to encode operations that this computer should do. It would have looked something like the picture on the left there. And this paper tape reader kept on misreading his code, which meant that he would submit it one evening and come back the next morning just to find a huge pile of paper tape covered with meaningless holes. And he thought, well, why can't the computer realize when it's made an error? This was his great insight, that computers are the problem, but they can also be part of the solution. And he invented this code. So here are the code words. I won't try to explain exactly how it's constructed at the moment. You can ask me later. But here they are. So think of your number between 0 and 15, and find the code word that corresponds to it. So it's a 7-bit long expression. And I'll ask for a volunteer in a moment to play this game. So if you think you're good at lying, please feel free to volunteer. Okay, who would like to play the game against you? It won't be very scary. I can tell you what questions I will ask. Who would like to go? Otherwise, I shall simply pick on someone. Oh, great. Okay, volunteer. Thank you. Come up here. Excellent. What's your name? Timothy. Hi, Timothy. Okay, so you've got your secret number. Okay. Do you know what code word it corresponds to? Let me get my slides back. Do you know which code word it corresponds to? Okay, are you good at lying? Well, we'll find out. So, what is the bit in the first position at the far left? You're allowed to lie, remember. It's a 0. Really? What's the next one, Timothy? It's a 1. I don't think you've got it yet. What's the next one? Okay, thank you. Then a 1. Then a 1. Then a 1. Okay. Thank you very much, Timothy. Now, we are going to decode Timothy's number. So, which of the code words up there does this thing look most like? What was Timothy trying to tell us? That perhaps we got confused or he lied, and one of the bits I wrote down is incorrect. So, which of the words up there does this look most like? It's 7. Yeah. So he had lied. I'm clearly very bad at telling when people lie. So, Timothy, your number was 7, and you lied in the second question. So, you see how we can play this game? 7 questions suffice. You might ask, can one do better than 7 questions? Could there be a really clever code that would somehow do this with just 6 questions? And the answer is no. I can prove that for you, if you like. It's one of the things that we proved in one of the courses I used to lecture back at my university. Then you could ask me at the end. But 7 questions is as good as it gets. So if you did it in 7 questions, well done, honor is satisfied. Now, what I want to end my talk with is, what was Hamming actually doing? He was programming a computer. Now, the story of computing starts early on. Ada Lovelace is the first person who realized, before computers really existed as things, that there could be a subject called computing. And she had this key insight that a computer could be a very general purpose device. It wouldn't just be a sort of completely static thing that did one algorithm, like a clock, that just tells you what the time is. She had the idea that computers could be programmed, and that you would write algorithms for computers. She cooperated with Charles Babbage, who had this dream of making a computer. He called it the difference engine, which would have been constructed entirely out of clockwork. And unfortunately, this thing was beyond the technical capabilities of the Victorians to make. It's not clear if one could even really make it now. But in theory, as a pure mathematical device, it would have worked. Another interesting example, Katherine Johnson. She was the first African-American woman to do graduate studies at Virginia Tech. She lived through the whole civil rights struggle in America. And her first job was as a NASA computer. Her job title literally was computer, because in those days, computers weren't physical things. They were human beings employed to do a big calculational task. So she worked on computing trajectories for the early space probes. And was, by all accounts, a very talented mathematician. And now we come to Turing. Turing's school report is here. His mathematics report makes interesting reading. It reads, but he must realize that ability to put a neat and tidy solution on paper, intelligibly and legibly, I don't know if the writer can really talk about legible, but anyway, intelligibly and legibly is necessary for a first-rate mathematician. Well, I couldn't agree more, because mathematics, it isn't just about numbers. When we write our research papers, most of the paper is words. Here's a slightly atypical example, but this is a genuine mathematics paper. Published in the top mathematics journal, one of the journals of the American Math Society. So this is a proof of a certain property about harmonic functions, whatever they are. But what I want you to notice is that there are no numbers at all. Okay, the number 2 appears, but it's missing out. So this is how mathematicians communicate with each other. You have to be able to write and explain yourself clearly. So Turing now is mainly famous for his work cracking codes in the Second World War. He had a brilliant combination of mathematical and computational insights that led him to a way to crack the German Enigma code. So I won't try to explain exactly what he did, but he had some mathematical ideas that meant you didn't have to search the entire key space for the possible key of his cipher. You could look in a strategic place, perhaps only looking at a few tens of thousands of possibilities. But this was still far too much to do by hand, at least if you wanted to decrypt everything. And one of the principles of intelligence analysis is that you read everything. You don't just read the U-boat shipping forecast. You read Hitler's laundry list. You read everything, and you piece it all together. And to do this, you have to decrypt on an industrial scale, which is what happened at Bletchley Park. And they use devices like this. This is called a bomb, spelled with an E on the end. And it's a special purpose device for attacking the Enigma code. It runs through these tens of thousands of secret keys, and it stops, and it's found the right one. And once you've found the key, using some small bit of your ciphertext, you're in great shape, because then you can decrypt all the messages that have been sent using that key for that table. So that's what Turing worked on. And his example, the example of Bletchley Park in general, and Catherine Johnson, as well as the ancient Greek mathematicians that I showed you earlier, they are all united by their love of truth and the pursuit of knowledge, even knowledge when it's hidden from us, either because it's been hidden by some kind of secret cipher, or because it hides in the mathematical world. It's out there, but we don't yet understand the mathematics well enough to explain it, either to ourselves, or, as I hope I've managed to do today, to others. So that is my talk, and let me end with Turing's most famous achievement mathematically, although perhaps less well known. So Turing proved this theorem, which I'm stating slightly imprecisely here, but I think it does give you an honest idea. So Turing proved that there's no algorithm that will decide whether a mathematical statement is true or false. Any mathematical statement is either true or false, but there's no algorithm that, if we encode the mathematical statement suitably in binary, as you've seen, everything can be encoded. You can't just feed it into a computer and get the computer to output 0 if it's true and 1 if it's false. There are fundamental limits to algorithms. So here are 4 mathematical statements. There are infinitely many primes. That's true. I proved it for you. You should be convinced beyond any doubt that it's true. I am willing to bet my life. I am willing to bet my house in Surrey. By British standards, this is more than my life. We were threatened with house price crashing Brexit, and look what happened there. It takes 4 bits to store a number between 0 and 15. This is true. You cannot guess the number, even with no lies, in fewer than 4 questions. There are infinitely many primes ending in 1. This is true. If you looked at those spirals, you should have seen that it looks like it's true. But it's much harder to prove. There's a way to win the liar game in 6 questions. That's false, and I can prove it. How about this one? There are infinitely many twin primes. So twin primes are primes that differ by exactly 2. So like 3 and 5, 5 and 7, 17 and 19. Wait 10 years and 2 will come along at once. 2027 and 2029 are both primes. Most mathematicians think this statement is true, but we don't know for sure, and we can't prove it. There was a huge advance recently where we got closer to a statement that's like this. This one is still open. Or how about this? There's a way to factorize really big numbers into their primes. So I showed you earlier that 30,031 is 59 times 509. You could have found that yourself, although it might have taken you a few minutes with a calculator. If I'd given you a number that's really big, you would have found it much harder to factorize it. But the difficulty of this problem is absolutely essential to the codes that make communication on the internet possible. Public key cryptography, if you've heard of that, depends critically on there being no fast way to solve this problem. But we don't know for sure. Maybe someone in this audience even, maybe you will find a quick way to factorize large numbers. If you do, give me a phone call. I'll tell you what to do next. Maybe as mathematicians, we will prove that no, it just cannot be done quickly. So, that's it. Any questions?